Ladies and gentlemen, it's very great pleasure indeed for me to be able to attending this meeting. I am Yin Bin and working at Meituan. I am deeply grateful for this opportunity provided by this conference to share the achievements of our team with everyone. Today I would like to present my paper, Heterogeneous Knowledge Fusion, a novel approach for personalized recommendation via large language model. In the first part of the report, I am going to begin with the motivation of my paper and introduce the methodology of my paper and then show the experimental results and last draw the conclusion of this presentation. The first part of my presentation will focus on the motivation of my paper. In recent years, the importance of analyzing and mining user behavior in recommendation systems has been significantly recognized. Particularly in the context of Meituan Waimai, we observe a heterogeneous nature in user behavior. This includes a variety of behavior stacks, contents, and signals. The prevailing approach in the industry involves incorporating these device behaviors into traditional recommendation models. However, this approach brings forth two distinguished challenges. Firstly, the vast area of behavior stacks results in sparse filter, making effective modeling a complex task. Secondly, the current practice of modeling user, merchant, and commodity behavior sparingly outlooks the potential of integrating heterogeneous knowledge among these behaviors. In a sense, we need to rethink our approach to ensure we are capture the full spectrum of user behavior while also effectively modeling and integrating this information. So to solve the above two issues using large language model, we propose our work HKFR. In this section, I will explain our work in detail. In the stage of heterogeneous knowledge fusion, we utilize the rich semantic knowledge and powerful reasoning ability of large language model to facilitate the integrating of knowledge. To address diverse user behavior, we extract and structure user behavior data. Then we design and construct different structured templates for device user behavior, expressing behaviors and templated text language. Next, in the knowledge fusion model, we explore large language model to prefer knowledge fusion on the behavior text, obtaining knowledge text. The heterogeneous knowledge generated based on user behavior will be used for the fine-tuning and recommendation stage of large language model. We leverage the large language model's ability to understand and interpret various forms of data. The model can then draw connections between these different pieces of information, effectively fusing them together. What's more, the large language model's powerful reasoning ability comes into play. It can analyze the fuse the information, identify patterns, and make prediction based on these patterns. This allows us to create a more accurate and personalized recommendation system. In other words, we are not just adding more data to the mix, we are using the model to make sense of this data, draw connections between different elements, and using these connections to make better recommendations. This approach is not limited to Meituan Waimai. It can be applied to any platform or system that relies on user behavior for recommendations. This makes our work not just innovative, but also highly visible and scalable. The fine-tuning process is all about making the large language models more adept and understanding diverse knowledge and boosting their accuracy and adaptability in making recommendations. Here is how we do it. We create an instruction dataset that's tailored to the recommendation task and the diverse knowledge we are dealing with. This dataset is made up of three parts: input, instruction, and output. The input is the diverse knowledge we have generated. That's all the raw data that the large language model needs to understand and integrate. The instruction and output are a bit more specific. The instruction and output are a bit more specific. Here are a series of task description and target results that we have created specific for the recommendation task. The instruction might include the recommendations for user preference on things like categories, price, and merchants, while the output is the actual label of the user's next order. Once we have got our instruction dataset, we start fine-tuning the large language model. We have chosen the open source model chat GLM as our base language model, and we are using the LoRa method for fine-tuning. In simpler terms, we are teaching the model how to make recommendations. We are giving it a bunch of examples, and we are using these examples to we can adjust the model until it's really good and making recommendations. And because we are using the LoRa method, we can do this fine-tuning in a way that's effective. Now it's recommendation. Given a user, retrieve user behavior from the dataset, then design instruction based on the recommendation task, perform reasoning and calculation, and output the recommended results for the user. These instructions include predicting user preference for categories, price, and other features like as well as their next click. The predicted results can be output and direct recommendations in natural language form, and can also be used as semantic features to enhance the recommendation effect by concatenating with the existing features in traditional recommendation models. Okay, now let's move on to the experimental results. After we have implemented the above process, we need to test it to see how effective it is. We will use a variety of metrics to measure the performance of our recommendation system. As shown in Table 1, our model significantly outperforms multiple baseline on the YMI dataset, demonstrating its effectiveness. When compared to traditional sequential recommendation methods, our model shows superior performance. This is largely due to the effective fusion of heterogeneous knowledge by the large language model. Our approach also outperforms language models. The fine-tuning of the professional datasets significantly improves the mismatch between large language model and the recommendation tasks, leading to the superior performance. We also constructed several experiments to validate the effectiveness of key modules in our work. When we compared our full model with no HKF, which removes the heterogeneous knowledge fusion stage, our full model shows superior performance. This suggests that the fusion of heterogeneous knowledge can actually capture user interest. Similarly, when compared to no-IT, which removes the instruction tuning stage, our full model achieves better results. This indicated that instruction tuning can effectively help model adapt to downstream recommendation tasks. In conclusion, these results evaluated the effectiveness of our model, demonstrating its potential for improving recommendation systems. Okay, the end is conclusion. We propose HKFR, a new approach of personalized recommendation, while large language model, which is based on the fusion of heterogeneous knowledge. By leveraging the two stages of heterogeneous knowledge fusion and instruction tuning, HKFR can effectively model user heterogeneous behavior. Extensive experience on the YMI dataset have validated the ability of our model to improve recommendation performance. In the future, we will focus on further training our model in the counting domain to better integrated heterogeneous knowledge and enhance recommendation performance. That's all. Thank you to the that's all. Thank you to the organizer for giving me the opportunity to share our team's work with everyone. Thank you for your attention.
Okay. Now, since this is just a video recording, we don't have any Q&A.